Okay. All right, so I'll kind of restart. So welcome everyone. Today we will see 3 presentations from everyone who's been in this very intensive and exciting, also fun process around learning how to build data-driven decisions, solutions, insights, dashboards. So we did a lot of things. And today we'll be hearing about 3 projects that the girls have been focusing on in the past couple of weeks. So with that, I'm going to hand it over to Michelle and Claudia to let you know about their project.
Okay. Hello, my name is Claudia, and together with Michelle, we are presenting our project. So we decided to create a recommender systems including different items. So we have different products such as Kindles, music, and movies. And I'm going to explain to you which models we tested, the limitations, problems that we experienced, and what did we learn from this project. Yeah, so this is the plan for our presentation. So first, we are going to explain a bit the data that we used, sort of the plan that we decided to, the rationale for how we decided to tackle issues, the challenges as well. Then we're going to have a look at how we explored the data available. And then we are going to go through the 3 different models that we created, namely popularity-based, 2 collaborative filtering systems, and then finally we'll have a bit of evaluation of the models and future recommendations as well. Okay, so essentially we downloaded data frames from the Amazon website. This was the sort of available, data on different products that Amazon sells. We went with music and movies and Kindles, as I mentioned before. I mean, we can also see the reviews for each of these sort of products. There were 2 documents, one which was a general data frame with multiple columns and variables, and a second sort of document that is not on here, but it was just the reviews. So we worked with both depending on what we wanted to do, and we'll explain that. So yeah, this was the Kindle sort of data set. Then the digital music, and finally movies and TVs. And as you can see, it included a high number of reviews, which was a challenge, and we'll explain why that was the case. So yeah, this essentially, all the data sets include sort of a ratings, of course, by real users. So Kindles was, so the satisfaction went from 0 to 5, 0 the lowest, 5 the highest. So we have Kindle average 4.2, music 4.6, and then movies, which was with 4. So relatively high. Which means that it looks good on Amazon as well, and its products, because they have a high rating, as you can see. Okay, so I mean, the reason why you might want to use and create a recommender system if you have a company such as Amazon is because you want to inform your clients or new clients as well what could be a right product to buy. And also, yeah, it sort of helps companies to target specific customers based on their needs and likes, dislikes, and reviews, and so on. So it's a good way, if for a company also to expand. Okay, so in terms of challenges, essentially the main thing that we experienced, obviously at sort of this level, was that because the data sets were so big, it crashed our systems quite a few times, which meant that we had to reduce the size of our data sets using randomization. So that means that we picked a million, I believe, different users randomly to just make it easier for us to analyze what we had. So yeah, these were in terms of the challenges, some. Okay, this is just a sort of a screenshot of essentially like uploading the data to our Google Colab. This was for, so if you remember, I said that we uploaded 2 sort of documents for each product. So this was for the Kindle, for example. This is the full data set. So here you have a lot of columns. So you have the overall rating, 5, for example, the ID of the reviewer. This is essentially the name of the product, summary, and so on. Another maybe sort of challenge that we experience is the fact that there's non-title. So for example, this was a Kindle, but all we could see was the ID of the product, and that was the same for films and music. So that was a bit of a problem because you are recommended essentially sort of an ID and not really a title. Then, yeah, we concatenated the different data frames. So as you can see, which is the same. And yeah, Michelle, sorry, do I see go or do you want to go?
No, I can continue.
Okay, sorry. Okay. So then we did a bit of data exploration. So this is what it looked.
I can go on.
Okay, yes.
So as Claudia said, since the data was so big, we had to sample it. So we had the very brief data exploration analysis to see if the distribution is the same. This is the original purchases by domain. So it was half of the ratings were movies, and then followed by Kindle books, and then digital music was the smallest data set. And can you go on the next one? And this is the distribution of the actual score given by the user. You can tell they are quite generous. Since the highest counts are for ratings of 4 to 5. For all 3 data sets. And no, you can go. And this is what we subsetted as. As Claudia said, we got 3 million ratings, 1 million for books, 1 million for movies, and 1 million for albums, I guess, for music. And the overall satisfaction is 4.4, which is actually very good, but for the sake of the project, we keep it going. And from the 3 million ratings, we have 1.8 million different customers and 670,000 different products. So of course, now the sample looks like that. Go back. Can you go to back?
Back or?
Back.
Sorry. This one?
Another one back. Yeah, so now the amount of reviews per domain is the same because we decided to make a balance between books, movies, and music. However, if you go to the next slide, the distribution of the scores is quite similar. Again, quite general, but since most ratings are between 4.5 to 5. And now Claudia will start explaining one of our first models, which is the popularity base.
Okay, So yeah, I'm going to introduce to you the popularity-based model, which is the most basic and simple recommended system. So I'm gonna give you an overview of what it does and when it would be a good idea to use it. So essentially, what the goal of this recommend popularity sort of system is that, as the name says, it uses popularity of items. So in this case, the ratings of Kindles, movies, and music to basically generate an output which is recommendations for clients, for users. It's essentially, it's also sort of it relies on aggregated data. So what that means is that every time a customer, a client, sort of likes an item or buys an item, that sort of click goes into a data set and it adds up. And so, for example, maybe for, I don't know, a book, you have 5 ratings, maybe from 2 customers, let's say, and so on. And so you use that data to check which products are more popular. So certain, like, for example, elements that you can use is, for example, how many times the item has been rated, which is what we did, as well as what is the average rating per item. So yeah, essentially this is what it does. It relies on popularity. Okay, so something maybe to sort of clarify is what is popularity and what do we mean by that? So again, it can rely on different things depending on the data set that you're using. Our was pretty limited because we didn't have the title and all we had was the sort of rating. We also had some sort of summary with some comments, but we didn't really use that. But yeah, so you look at the total interactions. So for example, sum of views, clicks, and likes. You look at which items had the highest sort of number of reviews, which one got the sort of highest overall ratings. You can look at frequencies, how many times an item has been bought, for example. And yeah, so you rely on these factors essentially. In terms of pros and cons, so I mean, it can be advantages because it's simple to use and it doesn't give many sort of problems. It's robust, which means that although your data might be very limited, it still works. It's helpful, like maybe even for Amazon, because if an item receives a lot of likes and has been bought a lot, then you as a data analyst, you can sort of deduct that this item is trendy and popular. It's also good for scalability, meaning that yes, it works well with a limited amount of data, but it can quickly be sort of expanded with larger data sets. For cons, because it just relies on, again, popularity and ratings, it's not very personalized. So you as a new user, all you see is what movie is, popular these days. It also neglects certain items because essentially maybe a movie is new and it's not that it's bad, but it just hasn't received many likes. And so it doesn't really recommend you that. It just recommends it's more likely to recommend movies and books that have been sort of on the market for a longer time. So yeah. So yeah, this is just a snapshot of how to measure popularity. So this is, as we can see, here we see the domain. So this was a Kindle. This were the most popular Kindles, actually. We can see like the number of sort of reviews. Well, not reviews, but ratings. This was for music and the most popular ones. And this was another way of looking at popularity. This is just the code where I use this formula. And essentially, this is called weighted rating, which means that because all of these products have a different number of reviews, and maybe some of them have less compared to others, it's really important that you normalize it, meaning that you want the system to still recommend, sort of take into account of the number of reviews and so on, so that it balances it essentially. And here on the right, we can see the most popular products. So we have CDs here, music, Kindles, and movies. Okay, this was, yeah, so because it's a very simple sort of system, the popularity recommending system, maybe if you want to add a bit of variety, you could sort of group it by, well, in this case, source, so the type, meaning Kindles or music, so that you could potentially, if the user wants to be recommended music, they can get that as well, and not just, just the most popular item across the whole data frame. And yeah, this is essentially, again, a snapshot of the code that we used. Okay, so now Michelle is going to talk to you about a different system, the singular value decomposition.
Okay. So this one is a collaborative filtering, and it's different from the popular base in the sense that it's going to make personalized recommendations. And it can be both user-based or item-based. Here it's, oh no, wait, never mind. It's both. This is both. So basically, can you go to the next one? It's about decomposing the data, the matrix that we have, and then reconstructing it again to fill in the gaps, let's say. So for example, this first matrix in the picture would be the user item connections we have. I think this user like this product or not. And we can find the algorithm similar to what we did with the principal component analysis, find the relation between all the users and all the items to fill in the gap. Maybe you can go next. So as cohort mates will remember, it's a supervised model, meaning we are going to split the data into training and testing sets. And then we train each model with the training data. You can go to the next one. And then we can make predictions by giving the model user and an item. So, I mean, it's not super clear here. We could have put a print in a sentence, but basically this user is predicted to like the product, well, predicted to score it as a 4.39, let's say 4.4. So it's basically predicted to like this product. However, to evaluate the model, you can go to the next one. We use test validation, meaning we're gonna do different subsets of test, of training and test, different polls, and we get the root mean square error. And this is basically going to give us the difference between what we predicted from the training set about the test set and how different it is. So how close we got or how far. In this case, I might be mistaken, but I think it's not so good because our scale is from 1 to 5. So the fact that the poll are like 1 unit away from the difference from the prediction and the reality. Let's say it's 1 unit. It's probably not ideal, but again, we have used very, very, very tiny piece of the data because of computation limitations and also time limits. I think that's it.
Okay, so another model that we use to sort of recommend products is called the key nearest neighbors. So essentially this recommender system relies on a machine learning algorithm, which is called key neighbors classifier. Essentially this algorithm is used for classification. So for example, when you want to even, for example, in images, in machine learning, they use this as well. What it does, so if we, for example, think of this question mark as the item, the product that we have, so for example, a Kindle, let's say, it looks at what's around it, and it calculates a distance between the item, so this Kindle here, and what's around, so the case. So the distance you can decide as a data analyst, depending on the size of the data set. But yeah, essentially, for example, here, it would essentially, so if we think that this is class A and this is class B, it would decide that this item, it goes with class B just because there's more in this circle. So yeah, this is the way it works. It makes a prediction, and then it basically like finds the items that are similar. So I'm gonna, it basically like leverages similarity between items to give recommendations. The way it works, I'll show you a code, but it essentially creates a matrix with the products, then run some calculation, and then you have the output, which is the recommendation, essentially. This is just a screenshot of the products. Another problem that we had is that I don't know what I did, but essentially I couldn't print out the sort of output. So there must be like a bug that I did not find. But fundamentally, as you know, here essentially this is what it should give you. Since you've read or since you bought X products, this is what we would recommend. But yeah, as we can see here, it basically created a matrix, and then this is the algorithm, and this calculates the distance with the other items in the data set. Now we go back to Michelle, which is going to tell us about the sort of evaluation and then some strategies for future sort of analysis.
Yeah. So as I mentioned before, to evaluate the good performance of the model, we would ideally compare the root mean squared error from the SVD and the K and M. Hasn't been possible this time. As I said, it's the difference between the predicted and actual values, meaning how accurate our model is predicted. And next slide. Another one. Yes, and there is this method of randomized cross-validation where we could do random different calls for as many times as we want, and then compare all the root mean squared errors and find the smallest one, and then use this specific code because it's the one that gives us the most accurate model. And also build hybrid models, meaning maybe combining neighbors with popularity or even with content base, which we started but does not finish. So apart from getting the similarity based on scores, we could, for example, find similarity between items and users based on features that we find in the reviews, in the text reviews, not just the score numbers. And once we would have this super personalized list of recommendations, we would, it's a marketing thing, I guess, define the diversity we want, meaning we would probably recommend to a user different prices, different genres, different domains at the same time, so the recommendations feel diverse. And well, this is the authors, I guess, from the data. It's what we had to cite. They were actually working on NLP, and they did the summary column. It's not ours. They took the review text and got the features, and created a summary. So instead of like 3 sentences, now it says amazing time, something like that. Oh, and the slides are also not ours, they're from Fred. Thank you.
Thank you, and congratulations for your work. Before I share my comments, I would like to ask if from all your colleagues, if you have any feedback, any questions, and from your audience, if you do want to ask any questions or provide feedback, feel free to use the chat. We will be keeping an eye so we can also answer your questions. And from your colleagues, is that anyone wants to ask any questions, give any feedback?
Awesome presentation. Very good.
Thank you, Jana.
All right, so I'll break the ice a bit, and then if you do have some questions, go for it. So first of all, I also want to bring some light on the challenges that Claudia and Michelle had. So when you heard the beginning of the story, it was around having a lot of data. And not only that, the data was structured in JSON files. So not at all times when we have a data-driven problem, we have tabular data coming to us. So actually JSON files are structured in different levels. So a lot of work was trying to figure out what do I want to keep, how do I read this data in, how is it structured? So that was one of the initial challenges on how to do that. Once that step was done, then another challenge came, which was around the computation power. So that's one thing for us to keep in mind, even though we keep hearing the news talking about the petabytes, huge machines and so on. But fact is, when we come back to our day-to-day journey, many of those models were pre-built models. But if we do want to take that massive amount of data, we need to have different strategies and also computation power. So the strategy there, and I think that's one of the great values from the project that both of the girls did, was about, I will take a sample of my data, and that sample is a representative sample of the products and the users, and I will see how good is the model that I built. And that's a very good strategy in general, because you start with small data sets that is, representative enough. You see that you are good direction. And then once you are there, and let's say you're imagining you are in a real scenario, then you can go to a big machine and deploy it there. But you are pretty confident that already the pipeline you have works well. And this is what we saw. And I think you also did a great presentation. I think you had a very good communication. It was clear, it was easy to follow. Even when we had pieces of code, it was good for us to understand a bit of the journey, how you went about it. So I really like that. I will repeat one thing that we talked about in the past, which is do not use words like basic or limited. Popularity on that example, popularity recommendation systems, we might feel like, oh, they're a bit simple or basic, but they're not really that simple or basic. Actually, as you presented, Claudia, we could see the underlying complexity behind, because then we have to put a logic like what is popular, but not only that, they're super powerful. So we need to keep that in mind as well. So that's just kind of a reminder, but also I really like the way that you presented it. Yeah, so I think congratulations. I think overall that's what I want to say. I really like the fact that you overcome all your challenges and you had 3 models to present, and you presented in a very nice flow and enjoyable manner. Thank you.
Thank you.
Thank you.
All right. Okay, and well, if you do have questions, you can always pop it up in the chat, and then we'll still be here, and Claudia and Michelle can get back to you. All right. So next, I think Seppi, Anna, you would like to go next, right? Yeah, all right. So we can see your screen.
Can you see the screen?
Yes, I think you just need to maximize it, that's all.
Just a second.
Perfect, yes.
Yes.
Go for it.
Welcome, everyone, and thank you for joining us today. We are excited to present our work on detecting car insurance fraud using advanced machine learning techniques. Jana and I chose to focus on car insurance fraud detection because it's not just a significant financial issue for insurance company, but it's also impacts honest policyholders. Moreover, it's one of the most challenging machine learning problems, and we love challenges. What does fraud in car insurance mean? So it basically means lying to the insurance company for financial gain. And car insurance scams range from staged accidents, exaggerated claims, false documentation, to vehicle dumping, and etc. And one of the most important means to decrease the number of fraud cases is to analyze the data that the insurance company collects for each case and use machine learning techniques to detect fraudulent cases and improve business decisions to reduce the financial loss. So what was our journey to achieve this? First of all, we explored our data set to find out any relationship between different features and fraud cases. Then we did some feature engineering, and because of the nature of these kind of data sets, because they are highly unbalanced, we used some resampling techniques, and finally, using this prepared data set, we trained, tuned, and evaluated our machine learning models.
Yes, so first, a little bit about our data set. It's essentially 15,000 cases of car insurance claims. The information that it contains, a single claim, is on the driver, things like the driver rating, gender, age, the things about the accident, for example, whether it took place in the rural versus urban area, information about the vehicle, whether it's a sports car, a sedan, a utility vehicle, some time information about what day of the week of the month in general the accident took place, and also when the claim was submitted, and things like the value of the vehicle. So all this constitutes the car insurance claim, and we have 15,000 instances of that. So using all these features, we want to build a classifier model that will, next slide, please. So we take all these features, we want to feed them into a classifier. We will talk about the models we choose to, excuse me, for this, the models we chose. And want to see how the classifier, how good classifier is in detecting the fraud. That is, we have one target variable, it's binary, there is either fraud or not fraud, there is no middle ground. And yeah, we'll talk about the models, but first we wanted to go first to the EDA and exploratory data analysis. First, we want to look at the target variable, which is fraud, yes or no. And immediately what we noticed is that there is a very imbalanced data set. So that is, there is more non-fraud cases, majority class, than there is fraud cases. So good for humanity, not so good for our model. Basically, it translates to 94% of the non-fraud cases versus 6% fraud cases. Next slide. Yes, so then this was the target variable. Now we want to see what is the, if there is overall association between each of the variables that we have and our target variable. So for example, if we take accident, whether the place the accident took place has any effect on the fraud. If it doesn't, then we would expect the same distribution, 94 versus 6 non-fraud versus fraud cases. However, if it does, we'll see, so this is what would we expect if there is no association between our variable, independent variable and the output. But however, if there is association, we would see that the distribution is shifted. So as we see here in the case of rural accidents, now instead of 6 versus 94, we have something like 8 versus 92. Okay, so then we look at the p-value for each of the tests, and the lower p-value would indicate that this difference is significant, and we would, and this variable might contribute to the number of fraud cases. Next.
So let's have a look what were our data pre-processing steps. We had our raw data set included 33 variables, of which 24 were categorical and 9 were numerical features. In order to prepare this data, we one-hot encoded our categorical columns, and we also had a look into each column, and we noticed that in the age column, we have 320 zero values. So we decided, which didn't make sense, obviously, for the age. And so we replaced those zero values, imputed those zero values with the average age from the rest of the data set. We also dropped few rows that had zero values in day of week of claim and day of claim, because they obviously didn't add any useful information to our analysis, and also when fraud cases. As you've seen in the previous slide, to understand which variables were most relevant to our fraud detection goal, we used the chi-square test. But after examining the data carefully and a few back and forths, we decided to keep most of the columns, as we realized that we want to keep the data as much as we can. However, we removed the age column because another categorical column with age of policyholder already exists in the data set, and we also dropped the policy number column because it's just an ID number and doesn't contribute to our fraud detection model. So with these steps, we ensured that our data was clean, relevant, and ready for the next stage of our machine learning process. But before diving into machine learning challenges, let's have a look into the columns that we have in our data set. As you can see in this pie chart, we have the sex of the customers in this insurance company. As you can see, 88% of the fraudulent cases were done by male customers, and then 11% were done by female customers. But bear in mind that the overall distribution of sex in this data set was, again, unbalanced. So most of the customers in this company are male. And we wanted to see if any car brand has more fraudulent cases. And as you can see, Mercedes won the game here. And in here, we wanted to see if we wanted to see the distribution of fraud cases in the areas, if it's more in urban areas or rural areas. And there's not much difference, I can say. And we had a look at the distribution of age. So we wanted to see if any specific age group is committing fraud more than others. And then we had a look at the vehicle price. So Yana and I thought that maybe if the vehicle price is higher, then the fraud is more possible, but that's not the case. Again, as you can see, the percentage of fraud cases in vehicle price less than 20,000 is higher than others. And also we had a look at driver rating, because we thought maybe if a driver has a lower driver rating, so they will commit fraud more, but that's again not the case. So this shows that the complexity of our data set. And another metrics that another columns that we had a look was the police, if police report was filed or not, and also if any witness was present or not. These visuals actually helped us to get a better sense of our data set and to identify if there are any specific patterns and trends in fraud cases. And as well as data pre-processing, because of the nature of our data set, which is a highly unbalanced data set, we needed to do one extra more step for this data set to be prepared for our machine learning models. And as it contains more non-fraud cases than fraud cases, to address this, we use data resampling techniques, which generally are called oversampling or undersampling. And you will see more of them in the next slides.
Yes, so for oversampling, we use the technique called synthetic minority oversampling, which basically takes the instances of existing instances of the minority class and interpolates between them, creating synthetic examples. So here you see the original data set on the left. The green dots represent the minority class, the fraud. And then in the middle, the red dots are the synthetically generated instances to balance off the data set. In the end, the resample data set has more or less the same number between minority and majority class. Yes, sorry, yeah. So just a quick thing. While it has obviously the advantages of balancing the data set that was originally naturally imbalanced, it also can introduce the certain bias in the data set and may not work for all the imbalanced data sets.
Yes, and another technique that we mentioned was undersampling. So basically we reduce the number of observations in our majority class, which is non-fraud cases. So by doing this, we are balancing our data set and having an equal number of cases in each fraud and non-fraud observations. But this also has its own advantages and disadvantages. So it can improve the accuracy of classification models on the minority class, which in this case is our fraud cases. but and it also can reduce the overfitting of classification models, and it's also relatively simple to implement. But the limitations are it can introduce bias into the data set, and I'm sorry, it wasn't the correct slide, sorry. So advantages was it can decrease the amount of data, and which can lead to speeding of the models to implement, and it can also improve the performance of the model on minority class, and it's again relatively simple to implement. But it can increase risk of losing important or representative information in our data set. So obviously it's not suitable for very small data sets, and it will also increase the risk of overfitting for the model. And as you can see, overfitting in here, the model is performing brilliant on the training data set. It catches everything, but that's also a problem because the model cannot generalize well on the unseen new data set.
So we decided on 5 different models to try. 2 of them, the single learning models, logistic regression and decision tree classifier. 2 ensemble learning models, such as random forest classifier and XGBoost, that can be used both on continuous outcome, but in our case, we use it for predicting the binary target variable, yes fraud, no fraud. And finally, we tried our luck with artificial neural network. The first one we tried was a logistic regression model. Logistic regression model is the classic, easily interpretable model because it's essentially a traditional regression formula inside the logistic function, and the output is basically probability. So it's very easy to interpret, and it's very easy to plug in the values from the specific data point and predict the outcome. So for example, looking at this formula and using our example, we can see that there is a decrease, the log odds of fraud would decrease by 0.15%, 0.15 when the claim is in the rural area. And it will decrease because there is a sign, there's a negative sign in front of the coefficient. Similarly, we can say that the log odds of fraud will decrease if by 0.35 if the claim is associated with the base policy of the vehicle being collision. So it's very easy to interpret, but at the same time, for the same reasons that it's so easily interpretable, it has its limitations. Because it assumes linearity between the different features, it may fail to actually capture some more complex nonlinear patterns between the features. It's also very sensitive to outliers, and again, might not work on all the data sets, especially if they're imbalanced. The next model we tried was decision tree, and Katie will talk about that.
Yes, decision tree, as the name suggests, is a machine learning technique that models decisions and their possible consequences, much like a tree with branches. As you can see, here's how it works in our car insurance fraud detection project. The decision tree starts with a single block, which is called root, which represents the entire data set for us here. And then it splits the data into smaller segments based on certain conditions or questions. Here, the question is witness present or no? And then it will also create branches and leads to more questions or conditions until a conclusion is reached at the leaves of the tree. For example, here in our case, the conclusion is if that transaction is legitimate or fraudulent. Decision tree has also its own advantages and limitations. The advantages are they are interpretable and they can be visualized in Python, and you don't need to normalize your data for these models. But they are also prone to overfit, especially with complex data sets, and they are also unstable. If you change the data set a little bit, the outcome might be very different in these models.
So next we moved on to ensemble methods. The two methods that they tried was random forest and XGBoost. The main difference between them is the algorithm they utilize. It's bagging in case of random forest, which means that the model basically constructs independent models in parallel, versus XGBoost, where the algorithm is boosting, that is, model is built in series, and each next model corrects the error of the previous one.
Yes, and random forest is basically an ensemble of decision tree, which I just explained. Imagine a random forest as a group of individual decision trees, each trained on a random subset of our main data set. So as you can see, we have n number of parallel decision trees. Each of them are doing their calculations, and then each of them conclude reach to a result, which is in our case if that transaction is fraud or not fraud. And each tree has its own output. Then at the end, we will have a voting based on a voting or averaging. We will have a prediction on that transaction.
At the same time, in XGBoost, you start with a simple decision tree, and then subsequent model uses the errors made by the previous model to build another sort of weak model. And this completes until, well, using the parameters you specified. And in the end, the final model is a weighted sum of all the weak models it went through. Finally, we tried also artificial neural network. So as a reminder, the model consists of several types of layers. The input layer where all the features go in. So in our case, it would be features like accident area, policy, the make of the car, then hidden layers, and finally the output layer where the verdict is reached on the outcome. So what happens is you feed the model the features, it then assigns weights and biases through the forward propagation. Then once it reaches the output layer, it calculates the error and sort of assesses the difference between the predicted and expected, and then propagates back to reassign those features. Yes, so now Seppi will talk about some evaluation metrics.
Yes, in order to see how well our machine learning models performed, we had to use evaluation metrics. And we chose to use confusion matrix. So confusion matrix, as you can see, is a table and that shows the actual values versus predicted values predicted by our machine learning. So as you can see here, for example, in this random forest model, our model correctly predicted 2,899 non-fraud cases out of 2,899. Very good. And 0 false cases here, which is again good. But our model missed to identify 182 fraud cases out of 185 and only predicted 3 fraud cases correctly. So it is a confusion matrix, as you can see. It is a powerful metric because it shows in detail that how our model performed in each class, and it's also the basis for calculating other important metrics like recall, precision, and F1 score. Recall is shows us how well our model identifies actual fraud cases. Precision metric tells us how accurate the model's non-fraud predictions are, and F1 is a balanced metric using both precision and recall metrics. So it's useful when we need a balance between finding as many frauds as possible and being right when we say something is fraud. For example, here we had a decision tree model and used a random sampling method in this model. As you can see, recall is here about 66%, which is not bad. It means 66% of our fraud cases are identified correctly by this model and resampling method. But if you have a look at the precision value, it's very low. So it means that the model is basically identifying every observation as a fraud, and which is also understandable from the F1 score here. F1 score is a balanced metric of precision and recall, and you can see the F1 score is really low. So our model isn't that good here.
So yes, to highlight again, the metric that would be the best to reflect the accuracy of the model is F1 score. So if you look at F1 score out of all models that didn't perform well, the best result we had was this XG boost using the random oversampler, which gave us the overall F1 score 0.24. What we wanted to point out is what would be wrong to use is the accuracy score, because since our case is about anomaly detection, just looking at the accuracy would be not very telling, or almost confusing, because we could say that the model is 88% accurate, but that would be very not true, because since what we wanted to focus is the detection of minority class, that is fraud cases. So unfortunately, none of our models performed well. We tried those 5 models, different kinds of oversampling, undersampling, combination of the two. We also tried different encoding. We went back and forth on our EDA. We combined variables, created additional variables. We also included some of the features into high versus low count, that is, used frequency coding, but unfortunately didn't have a Christmas miracle Hollywood end data science story. But learned an important lesson about the challenges that data scientists face every day in their life. And so in the future, or as a future direction, we would probably have to regroup with the stakeholders and check the quality of the data collection, perhaps discuss introducing new features. We did a little bit of brainstorming, decided it would be good to have things like the value of the claim, or the income of the driver, or maybe credit score, or whether they had a dash cam recording available during the time of the accident. You might want to expand the data set, especially include more fraud cases, or in general, more instances of the claims as well. and maybe do some additional segmentation, for example, focusing on specific age group first, and do model training on that subset. With that, thank you very much. You can find us behind the barcode, QR code, and thank you.
Thank you, everyone.
Thank you. Amazing presentation. Does anyone want to give any feedback, questions? It doesn't need to be only me. Any thoughts? The next presentation. Go. Sorry, Michelle.
I think you did a very good job communicating, because I was running through an airport and I still got your story that you were trying to tell, and also that no results or null results or negative results are also results, and I think we can see the smart work behind that model failure.
Are you saying you just listened to the presentation and didn't watch it? That's kidding.
I was watching too. I'm with my computer around the airport. I actually have to board, so I will have to watch the recording for Angela and Rachel. But I don't know. Good luck, and thank you, Filipa.
Thank you, Michelle.
Safe
Bye.
traveling. Anyone want to give any feedback? There's a lot of compliments in the chat about your presentation, your communication, and I have to say that was one of my notes that I had in here. I think you did a professional level presentation. It's clean. You did one thing that I really loved, which is go through the challenge of explaining complex models. You talked about neural networks, you spoke about assembly models, but you managed to have a visual and a walkthrough story that even if I'm not an expert, I can have a rough idea of how they are operating. And you did that across your whole journey, which is very well done. And it's not an easy task to do. Another thing that I really liked was your energy working together, and that was transparent as you did the presentation. We could see that you managed to coordinate, work in parallel, get together, and then have now your story to tell as a group. So I think that was also very well done. And bearing in mind that we are all in different locations, so you also had that additional challenge as you work together, and we could sense it. So that's also one of the things, data-driven solutions. And I would say in general, a lot of the things that we do, it's not an isolated work. So we need really to get on those skills about how do I share what I saw, how do I share tasks, and how do I put it together? And congrats, I also love that. And finally, now going back to the end of your story, because I have to make a comment on that. So many times we go and we see those challenges on platforms such as Kaggle, right? But we have to bear in mind that some of them are real world challenges. So it doesn't mean that we were going to pick up that lovely data sets and it's going to be, let's say, a walk in the park. But at the same time, we learn about those scenarios, right? So I think this data set that you got was a really, really very learning journey, strong learning journey, because you got to work with text, you got to work with numerical data, you had to be very creative, like how do I drive value out of this? So you did a lot of things in that. We did get a sense of that as you presented your visuals as well. And then thinking about what would be the model for this problem and how to work on that. And actually, just a call out here, and I do believe that you girls also share this on Kaggle, because if you go to this Kaggle where this challenge is there, so if you're curious, then ask here the group where it is, you will see that there's some, let's say, from the community workbooks that their models are amazing. And we're like, okay, so the group here went there, had some exploration. So when we are, preparing our training and test sets, you go through those steps, and sometimes they are things that can be misleading. So what we saw in there, in more than one person who shared their work, was that when they were going through the sampling strategies, they actually did the sampling strategy on the whole data set before doing the train test split. Now, that is a critical step that you should not do, because if you do that, it means that when you do the train test split, you will have very likely identical samples in the train and in the test for the fraud cases. So you also had that discovery. So always be critical critical thinking, like, okay, did I do it wrong? Did I miss something? Or maybe I can actually discover that I should, share my input with these colleagues that they are missing this bit. But yeah, congratulations, amazing presentation.
Thank you, Filipa.
Thanks for your comments, Filipa.
Thank you.
All right. So I'm just checking. Yes, there are no questions, but then again, you could always reach out to the group later as well. And with this, Rebecca, Rachel, Angela, feel free to share your screen and go for your presentation. Yes, we can see your screen, so feel free to start when you're ready.
Is that on presentation mode, Rebecca?
Oh, no, not yet, I think. Maybe it is, and you can see the top of the browser.
Okay, shall I start? Okay, hello. Welcome to our presentation. So we decided to focus our project on tree seedling survival and looking at how different plant traits and environmental differences might affect the survival. Rebecca, could you go to the next slide, please? So why do we care about seedlings? Well, seedlings grow into plants, which are important for the world, both ecologically and economically. Most importantly, they increase biodiversity by offering shelter and food habitats and habitats, food and shelter for different organisms. They also help stabilize the environment by mitigating soil erosion and regulating water cycles and nutrient cycles. They also can help tackle natural disasters in terms of forest deforestation, both human-made and disasters. And they can help mitigate climate change by increasing oxygen production and reducing CO2 or removing CO2 from the environment. And they also form an important role in agriculture. So farmers need healthy trees, which is used a lot in timber production and construction. So looking after them and being able to ensure that we have a healthy growth of plants is important for the world. Okay, next slide, that's you, Rebecca.
So our aims and objectives were to analyze seedling survival in a selection of 4 tree species. We wanted to look at and identify the key features that would affect survival, both external, such as light and soil source, and also biological features that related directly to the tree species. We then built machine learning models to predict the likelihood of survival of these seedlings. We're going to talk to you about our data source, where we got it from, and the study that it was based on. Then we'll look into our EDA, exploring seedling survival and the different factors that affected whether the seedlings continue to be alive or not. Then we'll go over the machine learning journey that we took. And then in addition to the machine learning, we took a look at survival analysis. And then finally, our findings and implications. So the data we used came from a field experiment that explored how tree seedling functional traits affect the survival of 4 specific species of trees. And the field experiment looked at a whole lot of factors, and some of these factors included soil source and light availability. The researchers that did this field experiment conducted it on a total of 3,024 seedlings. Now, our goal was not to recreate the study, but we wanted to focus our findings on particular features of the trees, particular features of what they were exposed to, and answer the questions of what affected the seedling survival rates. The data collection process of the field experiment consisted of the 4 tree species, which I'll talk about in a little bit, 7 different soil sources, a gradient of different light levels, because the scientists that conducted the experiment and us, we were interested in how light levels would affect seedling survival. And then they monitored the seedlings for 2 times a week over 1 growing season. And they looked at different functional traits of the seedlings and measured them and investigated how those affected whether they survived or not. In working on this project, there were a lot of key terms that the 3 of us had to learn and get familiar with so that we could understand the data set and so that we could kind of make sense of what we were dealing with. And these are terms that I don't think any of us had dealt with before, but we're pretty familiar with them now. So this table summarizes some of the key biochemical components in plants. This first one here, lignin, this is a class of organic polymers that basically help to give rigidity and strength to cell walls. And they provide a defense against soil-borne microbes, and they help also provide a way for water to be transported through the plants. This next compound here, NSC, non-structural carbohydrates, they're basically simple carbohydrates, and they provide plants with either an energy source. They help them respond to stress and environmental changes, and they're found in all plants, whereas this lignin is not found in all plants. And then finally, you'll hear us talking about phenolics. Phenolics are compounds that provide a chemical defense against soil-borne microbes. And these are also found in all types of plants. They help with UV protection, providing antioxidants, chemical defense. They basically kind of help boost the plant up and protect it. The data that we examined and the field experiment talked about different types of soil that was used. So 7 different types of soil were used for these seedlings. And some of the soil was conspecific, which meant that it came from the same species of adult plants. The other type of soil was heterospecific, so different types of adult plants were kind of grown in that soil. And we were interested in seeing if that had any impact on whether the seedlings survived or not. Talking a little bit more about soil, some of the soil was sterile and some of the soil was live. So basically sterile means that there was no microorganisms in the soil. And I was actually interested in how they get rid of all of the microorganisms, and what they do is they use gamma radiation. And the gamma radiation kills the microbes, but it doesn't affect the kind of composition of the soil. The other type of soil was live. And this can have all kinds of things in it. It can have all kinds of microorganisms, including this type of fungi AMF, which is found within the roots of the trees, and this other type of fungi called EMF, which is outside the root of the trees. And we were interested in seeing if there was a difference in the types of soil and whether having the fungi within the roots or outside the roots played any role in seedling survival. Now, here's a picture of the 4 species of trees as adults. And we wanted to show this to you because you can see that the trees are all quite different. They have different features, different sizes, different leaf styles. And the photos highlight that there's a difference among these trees. And it was an opportunity for us to see what factors were going to be common among the trees and what factors would be different in taking a look at their survival. Now, this is a kind of another look at the 4 different types of trees. It's showing you a few more insights about them, such as average lifespan, the size they typically get, survival tolerance, which refers to how resilient the trees are to different types of things like moisture levels and soil types, and then also growth patterns. There were some commonalities among these 4 species of trees. They're all found in North America. They're all deciduous hardwood species, and they have an ecological importance because they help provide habitats for wildlife. They contribute to biodiversity, and they also have a commercial importance because they're used frequently for timber. So different uses of timber furniture and things like that. So next, we're going to talk about our exploratory data analysis.
So before we moved on to looking at survival, we wanted to get a comprehensive understanding of differences or similarities in traits So the first one that we looked at was the differences in lignin, non-structural carbohydrates, and the phenolics between the species. And what it suggested are intrinsic differences between the species, with the oaks represented by the red and the grey boxes being notably higher than the cherry or the sugar maple, particularly in lignin concentrations. What was I going to say about that? Which might be related to like the functionality. For instance, lignin is involved in strength to the plant, so it might be that it allocates more importance in having high levels of that compound compared to different plants, other plants. In terms of the proportion of phenolics as well, there was a notable increase, or a higher proportion, sorry, of phenolics in the oak species compared to the cherry and the maple, which is related to plant defense. So again, another intrinsic difference is that it might be allocating more resources to ensuring it's better protected against diseases, pathogen intrusions. The distributions, looking at the box plots with the oak trees, we found that there was much more variation or spreads in levels around the mean compared to the cherry and the sugar maple. However, looking at, like, if we look at the interquartile ranges, it sort of suggests that the phenolics and the lignin levels are sort of might be significantly different compared to the cherry and the maple. Anything else about that? Nope. Next slide, please. Oh, so we also wanted to look at the influence of light on plant traits, and one of the key things that came about were that levels remain consistent across different light levels, suggesting that it doesn't really seem to, like, in terms of biochemical traits, light doesn't appear to be affecting levels. However, with the microbial associations, that's looking at the EMF fungi and the AMF fungi, there's some indication that increasing the light affected the percentage of colonization on the roots, particularly for the black cherry, which is associated with an AMF microbe. To note, with the EMF, so not all plants are have the same associations. So the sugar maple and the black cherry don't have any EMF microbes, whereas all the other ones do have AMF. So it shows that plants might have different microbial associations, basically. What else? That's it. Next slide, please. So we also looked at, as Rebecca said before, we have heterospecific and conspecific soils. So with the conspecific, it means that the plants are grown in soils that had species-specific microbes in it, whereas with the heterospecific, the soil could come from different plants. So it means that it has different microbes associated with it. And what the EDA suggested is that it didn't appear to be having a difference on any of the biochemical trait features. Yeah, that was it. And then the next one, please. So we also did some pairwise plot comparisons to look at interrelationships between species, and the key things that came out of it were an arguable bimodality between the species in terms of the biochemical traits, with the lignin, sorry, not the lignin, with the cherry and the maple trees, not only lower, hang on, let me get this right, so there's a biomodality in the species distribution. So they have the cherry and the sugar maple have lower biochemical traits, and they also seem to have positive associations with each other. So increasing lignin or increasing NSE resulted in an increase in another biochemical trait. Whereas with the oak species, what we found is that there's a negative association between the lignins that's involved in the strength and the phenolics and the structural carbohydrates, which again might stem back to sort of intrinsic differences between how the plant species grow. So the oaks arguably are putting more effort into the structural strength of the trees compared to the sugar maples and the cherry, the other one, the cherry thing. Positive scatters between light and oh yeah, so another thing that was very apparent with our pairwise plots is that light had a positive association with all the different features, suggesting that it is important for everything, and that in terms of the AMF and the EMF roots associations, that there's an arguably a positive association with all the traits if the plant has EMF root colonization. Next slide, please. All right, moving on to Angela now.
Hello, everyone. I'll be presenting machine learning. For our project, we concentrated on the left side of of machine learning. What we have is a supervised problem because we know the outcome, which was the event to predict if the seedling is alive or if it's dead. And this is also categorized as a classification problem. Next slide, please. So we found machine learning to be applicable to our problem in that it would help with the predictive analysis to predict the likelihood of a seedling surviving or if it's going to die. And because we are looking at different species, machine learning would come in handy in recognizing the different patterns between the different species, and it would be able to be optimized to improve the performance and help in decision support based on what the outcome of our model would be. Next slide, please. So our data set had 24 features, 24 columns in total, with 2,873 rows, which is the composition of our data set. And it comprised both categorical and object variables, as well as some integers. So most of our features are based on the data that was collected from the study, and the key terms have been defined in the previous sections. Next slide, please. So in coming to the machine learning and model building, we had to do a bit of data cleaning. And our study was a bit very scientific in nature. So we had to rename part of the columns from the botanical names to English names like the white oak and the red oak, names that we could understand and relate with so that it's easier to understand and to pronounce. We also checked the features to identify columns with missing values. And we noticed that EMF had missing values, but when you come to the biology of EMF, which is on the outside of the roots, the fungi on the outside of the roots, we found that it's not existent in all different tree species. So we imputed the missing values to be 0. And there's also for event column, it had one missing value, and we took that to be 0. And we also noted that the live column had over 2,000 missing values of 2,700 total labels. So for the start, we imputed that with 0, where alive means that that particular tree is alive at the end of the second growing season. Remember, our focus is the first growing season, and that is when most of the data set has been collected. So approximately 2,300 features were missing, sample data sets were missing. Also, the harvest column also had over 2,000 data sets missing, and we also imputed that with 0 to mean that that particular ID or particular tree was not harvested. We also noted that there were negative phenolic values, and we thought it didn't make sense to have a negative value, so we imputed that with a 0. Next slide, please. So during the data preprocessing, because machine learning requires numerical figures to be further computed to understand, and we had a lot of string variables, like say harvest was filled with X's for a data set that has been harvested and 0 for one that hasn't been harvested. So I had to convert that string to integers, like 1 would mean it has been harvested and 0 has not been harvested. We also had the date that the seedlings had been planted, and it was an object, so I had to change it to date time for the machine learning model to be able to understand that, and as well as convert some integers and objects, like say event had been changed to 1 and 0s, and 1 would be considered an integer, but with respect to our model, we'd want it to function as a categorical variable. So we changed it to categorical data type. We had tried machine learning with all the different features that had been provided, including the harvest and the live columns, but we noted that the accuracy was really high. So we thought harvest and the live are leaking information to the machine learning model. So we decided to drop the columns for harvest and the live. Furthermore, the 2 columns also had a lot of missing data, so it made more justification for us to drop them. The number was an ID for a particular tree or seedling that had been tested, so it also wouldn't provide much information to our model, and we thought it best to drop that particular feature. We did one-hot encoding for the categorical features, and we had a lot of them. So yeah, that's a lot of one-hot encoding to do during the process, the data preprocessing. Next slide, please. So once the data cleaning was done, then we had to go through the train test and splitting. Our target variable is the event, which classifies the outcome as to if the seedling is alive or if it's dead. And all the other columns that were left after we had dropped what we think was irrelevant were considered to be the features or our independent variables. We considered a 75-25 split, and then we did standardization on the trains set first and used that for the machine learning models. So because our problem is a classification problem, the models that you would have to use are logistic regression, decision tree classifiers, and the random forest classifier. We also use principal component analysis a little later on to help us in reducing the number of features and determine the survival analysis. So I realize Yana and Sepi have already explained part of the classification, but we are going to find another way to rephrase it. And so logistic regression usually has 2 outcomes. Okay, in our case, it had 2 outcomes. Either the sample is alive or it is dead. So I took dead to be 0 and alive to be 1. Logistic regression works in the way that you have, in our case, binary, just 2 outcomes, either 0 or 1, and then tries to fit an S-curve over the samples. In computing it, it will give you a probability such that any value below 0.5 will be taken as 0, and any value above that will be 0.1. So yeah, it just fits a sigmoid curve over the parameters. Next slide, please. Yeah, Rebecca will help me explain decision trees and random forest classifiers. Thank you.
So we also used a decision tree model to explore our data. And as you know, decision trees use a kind of a flowchart or a tree formation to make a series of choices and reach conclusions. And then those conclusions are pooled at the end to provide a predicted outcome. This root node here, which is at the top, represents the entire data set. So in our case, after we had done all of the cleaning and the pre-processing and had narrowed down the features that we wanted to include, that was there in our root node. Each of these little decision nodes provide the individual decisions. The branches connect the decisions, and then eventually these leaf nodes at the end represent the predicted outcomes for whether, in our case, for whether the seedlings were alive or dead.
Next slide, please. Okay, so this is an outcome from the decision tree classification, where we have phenolics at the very top at the root node. The Gini figure represents how good the split is, the quality of the split. And at the start, it has all the samples, 2087, which are in the train set. And these have been split into whether they're alive or dead. So this will be split into to the left. I hope everyone's the blue side, the blue one. So you have time. In this case, time is the point at which the sample was tested. Testing to determine if it's alive or dead, and also measuring the structural traits, that is the lignin, phenolics, and the non-structural carbohydrates. So if you're to go, I'll try and use the shortest one. So we shall go to the left, the orange one. Census is the number of times when the test was done. So the Gini, which is the quality of the split, is 0.37 for the first one, and it has 967 samples, and all of these are alive. And this was further split into another node, and we have, I'll stop at the last one, with a Gini of 0, and you have 359 of those samples are alive. So we put a maximum depth of 3. So the decision tree process would have to continue up to the maximum depth of 3 and give us an output. Next slide, please.
We also used a random forest classifier for a machine learning portion of the project. And we asked again, is the seedling going to be alive or dead? Random forests can be used for classification and regression problems. And they basically involve a group or ensemble of decision trees. And each of the decision trees is built independently, and they are trained on a random subset of the data and also a random subset of the variables. Each of these individual decision trees predictions are then combined. And then for classification problems, the outcomes are considered and basically voted on, you can see it that way, and the one with the highest number wins. Whereas for regression problems, an average is taken because it would be numerical. Random forests generally perform really well in a lot of data sets, and as Angela will explain, it performed very well for our data set as well.
So for the performance of all the different models was evaluated, starting with logistic regression. The performance is based on precision, where precision is how good, what was important to us for this particular data set was the recall parameter to determine how good our model is, where recall is concentrating on the amount of true positives and the false negatives. We want to ensure that we minimize the false negatives, where false negative in our case would mean you have a seedling that is alive, but the model has predicted it to be dead. So we don't want to lose out on any of our seedlings. In the case of precision, it would be concentrating on getting more the false positives, and that is not so much our focus. So we concentrated on the recall parameter for the different models, and we found that the random forest model scored the highest of all the 3 models that we're looking at. Our test set consisted of 290 data sets to be alive and 406 to be on the dead side. And so it was imbalanced in a way. Next slide, please. after we had decided what our best model was, we decided to optimize it. Our best model was the random forest. So in doing the hyperparameter tuning to optimize the random forest, we used the grid search method. And during the hyperparameter tuning, you'd have to look at different parameters and try to come up with the best. Would note that in doing so, it is subjective. It is subject to the parameters that you have chosen. So you can't necessarily say this is the actual best. Someone else would get different things depending on what it is they have considered. So in choosing the parameters to look at, we also thought it wise to include the default parameters that have been included in the model. So N estimators represents the number of decision trees that will be looked at for every random forest that will be checked. And the maximum depth, in simple terms, I would say is the different levels in the decision tree. And the minimum sample split is the sample that would be left at the end of the last leaf node, at the leaf node. And the minimum samples leaf is the minimum number of samples in each leaf. Cross-validation, we used a number of samples to be 5, so that the hyperparameter tuning is done 5 times. And our scoring was taken to be the recall, because that is what was important for us to determine if a model is good or not. So once we did the hyperparameter tuning, we got the best hyperparameter from the model, and it gave us a maximum depth of 10 with a minimum sample leaf of 1 and the minimum sample split to be 10 with 100 decision trees. The hyperparameter tuned model gave us a recall value of 0.96, which is slightly less than what we had obtained earlier on, but we also note that it has been done on several values, so it is a bit more reliable. Next slide, please. So after we had done the hyperparameter tuning, we went on to do, we went to do cross-validation and in a way find better generalize our model so that it is better suited to say if it's used on a different test set. And the number of folds that we used, the 5, we also note that the value would vary depending on the number of folds that you use. So in cross-validation, you'd have your sample split into, if you're using 5 folds, it would be split into 5. And then the model would pick like a subset from each of these 5, pick a sample from it and keep one for testing, and analyze the performance for all those different sets, average it out, and that would give us the value, the mean over those folds that have been analyzed. So once that was done, we obtained a recall value of 0.97 and a standard deviation of 0.013. So in essence, it would mean that our model generalizes well to new data. Next slide, please. So after we're done with that, we decided to experiment a little further and thought maybe if we looked at, say, an idea where you do not have to harvest the seedlings, because in harvesting the seedlings, you're indirectly killing them. So we thought maybe let us drop the functional traits and see how well our model would perform. So in model 1, we have all the functional traits, while in model 2, we don't have the functional traits. It's based mostly on the conditions under which the seedlings have been grown. So we went through the same process for model 2, and these are the recall values that we obtained for the different classification models. And we find that the values are comparable to when we use the functional traits. Next slide, please. Thank you. Rachel will be taking over. We did try to experiment and go a little deeper. So we used a bit of PCA to further justify our findings from the model, and Rachel will be presenting this.
Yes. So we haven't actually shown what anything looks like yet, or talked about what the survival can show us between the different species. So using Kaplan-Meier estimator curves, we try to just visualize. So these aren't machine learning techniques. These are just techniques that can be used to help give you a basic understanding using time to event data. And what it sort of showed or suggested, again, reflecting what we've been talking about before, are higher survival probabilities for the oaks compared to the maple and the cherry. Things to note here are that during the study period, which was over about 4 months, the cherry maple and the black cherry and the sugar maples pretty much reached 0, whereas the oaks typically didn't make it to 0, suggesting that they survived over the course of the study. And we have some mean survival estimates using this, which is sort of limited because of the problem of our oak trees not actually reaching 0. Next slide, please. And so we also looked at the survival analysis by grouping survival by things such as phenolics, the microbial associations, light, and soil type. And again, what sort of emerges is this idea of the key predictors potentially being the impact of phenols and the type of root association, with higher survival indicated with plants associated with EMF microbes. Next slide, please. And then what we did is we applied a semi-parametric model that took into account the impact of the covariates on the seedling survival. And if you go to the next slide, what we tried to do is use machine learning, so use PCA to reduce the feature complexity to make predictions on survival times. By grouping things like the soils, the spatial data, and the microbe data, and then fitting these features to the model, what it showed are that so that with our hazard ratio, basically anything that is negative suggests increasing survival with increasing of these traits. So phenolics and microbes, increasing levels in these two would increase survival. And anything that is positive would be deleterious to survival. The thing that sort of emerged from it is that actually the survival times were all quite similar, even though we might have expected plant species that had or demonstrated higher biochemical traits. We might have expected them to have longer survival times, but actually it's quite consistent. And oh, that was it. Sorry. So we've got the concordance index as well, which suggests that shows how good these models were. So numbers, we want the number as close to 1 as possible, which will indicate a better performance. And also the ones in the blue squares indicate significant statistical differences. And that's it. Next slide. So who wants to do findings and implications?
I'll do it. So as we talked about, the random forest model performed the best with this data set. And as Angela explained, we modified our data set after the first pass, and it still was the best performer. And it makes sense when you think about how random forests work and how they are able to take multiple decision trees and kind of kind of correct themselves and give you the best possible performance. And that's what happened here. Going into it, I think that we expected that there was going to be a greater difference in the survival rates among all the 4 species. We kept thinking that's what we were going to see, but then after we did the survival analysis, we saw that despite the trees' differences and the different biochemical traits, they all had very comparable survival rates. And as far as the implications for that beyond this, it seems to show that there could be more uniformity in forest management and reforestation efforts without having to cater to specific species of trees. It also, one of the findings that we thought was very important too was that light didn't seem to have that big of an impact, or the type of soil. And so these were takeaways from the machine learning and the EDA that were meaningful for us. Anything else, Rachel or Angela?
No, I think that you've hit the nail on the head. Next slide.
So these are the references, the data set we used, and then some of the literature on the underlying study, the field experiment that was conducted with the trees. I don't think any of us were super familiar with trees to that extent, but we learned a lot, and it was actually super interesting. So we read a lot of things about trees, and yeah, thanks for listening.
Thank you. Well, again, amazing presentation with a very nice flow. So before I go again, anyone wants to give any feedback, comments to the group?
Very jealous about the model performance. Very jealous.
I mean, actually, there was a slight issue in that Rebecca, you didn't get quite right, in that the light actually was the most important feature when it came to fitting the Cox proportional models, and that unless I took it out, the models wouldn't work at all. So it left it too late to be able to look further into what was going on there. But the light was important, but I think it was so uniform amongst all the species that it maybe wasn't, I don't know. There was something else going on.
I also like the way you went into detail about hyperparameter tuning. I really liked it.
Thank you. I like everyone's presentations.
All right, so I just want to give some comments. So first of all, congratulations, of course. And just picking up on what Jana was just sharing. So sometimes it's like the other way around. Imagine you run your model for the first time, and when we were here at the group talking, oh, the model is too good. Is this right? And I think that was one of the moments in the beginning. And then also when you have like such a good model, you start wondering like, oh, but I would like to try to improve it. Do I have room for improvement? So that's another real world scenario that sometimes you actually can get a data set with such a strong predictors in terms of the features that you're working on, that in fact, you would like to explore a bit more or make a bit more of complex solutions that maybe it won't nudge much. So I think we actually, in these 2 different projects, we managed to see that as well. And I think it's also a very interesting journey. Another comment that I had here is like, again, you did a very good work on explaining something that is super complex. I mean, I don't understand either about trees up to that level of that data set. And you started your presentation in a very easy to follow, even if someone is not an expert on trees, but it gives a good explanation about the collection of the data, how it was done, and what do you have to work with. And that's not an easy thing to do. And I saw your journey as well, and I think you nailed it really well, and you communicate it really well as well. The other thing is the strength of your project. So you did a very complete end-to-end journey. So you did the feature engineering, you work on all of that, you selected a few models, and then given that you already had a very good model, then you were able to do the hyperparameter tuning and explain the rationale behind. So why would I do the hyperparameter tuning and then make sure that it's robust with the cross-validation? So I think it's a very good end-to-end story, and you did it really well. So congrats. Thank you for sharing with everyone. I will be sharing with all of you my notes later on Slack. Any questions, let me know. I will be asking you as well to share your presentations with me, so we can just keep the presentations from all of you. And yes, so I do invite you to share with all of you and ask questions if you want to share the code, the things you've done. Keep in mind that you've seen it. There's so many different data science problems that you can work on. So you saw the presentations for your colleagues, learn from each other as well. So I would advise you to do that too. And I see that you still have some attendees with us. And again, there's a lot of compliments from your work. So if there's still any questions that you like to ask, you go for it. Otherwise, thank you so much for joining and listening in to this 3 amazing presentations. And yeah.
Thank you, Filipa. I think we should all thank you because it was great having you in the final leg of our bootcamp.
Journey.
It was very good. Yeah, thank you very much.
Thank you so much.
Yeah.
And now best of luck for everything that's to come, because I know that it's something, a few more steps. And well, you know, feel free always to reach out to me if there's anything that you like my support. And yeah, thank you so much.
Thank you,
everyone.
Thank you very much.
Well done, everyone.
Bye.
Well done. Bye,
See you later.